AI isn't just scaling, it's fragmenting. New compute models, new interconnects, chiplets, custom silicon. But here's the real question. How do you turn all of that into a working system? In the latest episode of Tech Threads, we sit down with Ian Ferguson, Vice President of Vertical Markets and Business Development at SiFive, which this month announced a $400 million raise with investors like NVIDIA lining up. So in this episode, Ian will help us unpack the future of AI systems from his vantage point, all the way from architecture decisions to full stack solutions. Stay tuned.
Welcome to Tech Threads, Weaving the Intelligent Future, the podcast exploring the fast-paced world of technology. In each episode, we dive into the latest innovations in data movement, AI acceleration, and the transformative potential of chiplet technology. Join us as we explore the breakthroughs that shape the future of computing and hear from industry experts on what's coming next in the tech landscape.
Hello, and welcome to Tech Threads, where we decode and prognosticate on systems shaping the next generation of compute. I'm Nandan Nayampally, Chief Commercial Officer here at Baya Systems. And in today's conversation, we talk about the shift that we're all seeing, but maybe not fully understanding the scope of yet. Because AI is no longer about faster chips or the war between GPUs, CPUs, NPUs. It's really about architecting complete solutions across compute, across memory, across interconnect, and software. And joining me today is Ian Ferguson, Vice President of Vertical Markets and Business Development at SiFive, who's at the center of that transformation. Ian is responsible for accelerating SiFive's growth across a range of segments, including data centers, consumer, and automotive. And of particular focus is how actually AI, or artificial intelligence, offers an opportunity for industries to shift from the incumbent architectures to the RISC-V based open standard. Prior to joining SiFive, Ian worked at Lynx Software Technologies as the Vice President of Marketing and was responsible for all aspects of outward-facing presence for the company to its customers, to its partners, press, analysts, and other communities. Ian also spent nearly 11 years at ARM in various senior roles, where I did have the pleasure of working with him. And Ian's a graduate of the Loughborough University with a bachelor's degree in electrical and electronic engineering. Welcome, Ian.
Hi there. How you doing? And most of the time when we were at ARM, we got along, right?
Yes, we tried. And there'll be stitches coming throughout the call.
There you go.
So, to kick off, firstly, Ian, not just thanks for coming on board, but congratulations on the massive $400 million raise that SiFive announced a couple of weeks back. I'm sure the team is energized. Can you give us a little bit of a flavor about what does that enable that wasn't possible before? And actually, what is the ambition of SiFive beyond where you are right now? What are you trying to unlock?
A few things in there to unpack. So SiFive was set up 11 years ago by several of the folks that are in University of Berkeley that invented RISC-V architecture. Krista Asanovic, Yongsuk Lee, Andrew Waterman. And you're exactly right, as you said, open standard architecture. So on some level you say, it's just another processor architecture, right? But it is that open standard, and I think maybe to be controversial at the start here, where our old place, people said, ARM, it's low power, that's really why ARM took off. To me, it was really a change in business model. And it was about the fact that instead of buying chips, ARM's model enabled other people that were maybe closer to the use case to build chips. And I think what's changing now is building on top of that is people wanting more control over their supply chain, not wanting to be locked in. There's all this sort of sovereignty, sort of in Europe for Europe, in India for India kinds of activities. And so on one level, you can do anything with RISC-V. It's incredibly flexible. On another level, it's incredibly rigid. We provide profiles, so basically an equivalent of something like ARM v9, so a set of mandatory instructions that the software ecosystem can line around. So that's a little bit of background. If you think about where RISC-V has been up to this point, if I go back a couple of 100 years, and I am old, but I'm not quite that old. If we think about back to sort of English gentry and houses, there were the lords and ladies, and then there were the under the stairs people. And those under the stairs people did incredibly valuable work, but they were seen and not heard, right? And they were doing kitchens and cleaning and things like that. And if you think about where RISC-V has been right now, it's been behind the scenes, working in smartphones, working in storage systems where those cores aren't exposed to software programming and things like that. They're just doing other tasks. And really what's changing now is, I think, RISC-V is getting to that place where it can become something in the main dining room, if I carry on with my analogy, and can be speaking at the dining room table and has value in there. And really what we're looking to do with this funding raise is to actually go off and accelerate the applicability of our implementations of RISC-V into that data center area across the world.
Now, that's pretty cool because, as you say, RISC-V so far has been seen more in solving a lot of the background problems rather than going front and center. And the original view is probably that RISC-V makes more it into consumer and maybe even mobile towards the mainstream rather than data center first. And it's quite a turnaround, if you will, right? And I see that the industry is changing before our very eyes, right? And AI acceleration, especially with new interconnect models, new architecture, are driving some of that change that you mentioned. And so if we zoom out, obviously you're seeing some of the changes coming. So what defines the next generation compute system?
Firstly, let's say I think it's not look at my CPU versus your CPU. There's a lot of column inches written about the CPU wars and, RISC-V is going to take over ARM, or ARM's taking over x86. I think the first thing to think about here is it's a system level thing, right? And people are needing to optimize a system for what they're wanting to accomplish. And increasingly that's, yes, you've got to have very capable CPUs, and you've got to couple those together very cohesively, coherently. But you've also got to look at the other elements of the system. These AI systems take a huge amount of memory, right? And sometimes you actually need even more capability than is in one particular platform. So I think at a top level, the first thing you have to think about is that system level and balancing what you're trying to accomplish with, what do those models look like? Memory subsystem, are you doing it all in one memory subsystem in a particular chip, or are you covering that across multiple systems inside a rack? Are you going across racks? So I think certainly we're seeing people put more and more CPU cores together. I mean, you're going to see hundreds of CPU cores, and people can start to get all excited about the CPUs in its own little micro world. But I think the first place we should think about is at that system level, given that workload, how do you balance all those pieces together? Does that make sense to you, or do you disagree?
No, I think it's great. In fact, what I see here is also the flexibility and extensibility that kind of comes alongside the different types of compute required, right? So there are accelerators, there are GPU type setups, there's neural processors, and each of them needs some level of compute that's more standard CPU-like. And I think RISC-V probably provides you with a lot of that flexibility to solve these kind of changing problems.
Yeah, I think so. I think the other thing is, and you and I know we worked through the early phases of exploration with ARM servers, a long time ago. A lot. If you think about servers back then, and when it started that work, 2008. There was a lot of very sticky software tied to the x86 architecture, right? And what's really changed in a number of these data centers is there's certainly more use of open source stacks. And I think when you come into the world of AI, you've got even more opportunities for new people to play because you're writing up to a standard API, whether that's PyTorch or TensorFlow and things like that. And then underneath that, you can go do some of your own magic things. Now, if you do custom instructions that the RISC-V instruction set allows, or if you do other things inside an ASIC subsystem of your own, you're going to have to own keeping that software capability updated, so the software knows how to optimize for that heterogeneous environment. But you're now not worrying about having to port every single application native, and that's, I'll go on record and saying I think it's going to be a long time. I think I'll be dead before we see a RISC-V based mobile phone, because you've got hundreds of thousands of apps that either you've got to translate on the fly into a new processor architecture, and then you've got all sorts of issues on power and performance associated with that, or you've got to port all of those things native. That ain't happening soon. So, but if I compare and contrast that to where the data center area is, I think it's a very rich space and opportunity for innovation, because we are getting to a world of optimized for purpose compute, right? And it's not just the CPU core, it's how you match everything together. And I know from watching a couple of your previous episodes of this, Nandan, it seems that every episode we have to talk about Jensen now, right? So I was at, we're recording this on April 20th. Cadence Live was last week, and Jensen was on stage with the CEO of Cadence, Anurag, and he talked about how he was expecting that how leadership would work in engineering on a forward-going basis is engineering groups would be assigned a whole load of tokens, and they would be measured. It wasn't going to be group's effectiveness wasn't going to be measured on number of engineers and things like that. It was going to be how effective are you using these tokens. And so the other part of the conversation last week was tokens per watt, and sorry, tokens per dollar. And I think that's one view. I think you're also going to see sort of metrics like total time of execution of a particular task. You're going to see sustained performance of tokens depending on the environment that you're in. But with that level of business motivation, and I would say this is one of the mistakes I made when we were at ARM thinking about the transition and getting people to convert from x86 to ARM, and we were talking all about the tech. At the end of the day, it's about the business. And so if there is a motivation to shift that token per dollar metric by a little bit, and by Jensen's number, he said he thought he'd be spending billions of dollars on tokens in order to stay ahead. Just a little bit of a dynamic change on what that dollar cost is going to motivate people to go off and change that little bit of software that's needed. And I think that's a very different metric on why people might look to shift architectures as opposed to something like a mobile phone, where there isn't quite such a business motivation behind it.
No, I think that's well put. I do think that each of these architectures will survive in their various pieces. It's not going to be one or the other. It's going to be actually a combination of all, right? And
yeah, I'm certainly not one that's predicting the end of ARM. They've built out good work with Amazon, with Graviton. They've launched their own CPU cores. So I think really what this is about is enabling choice across the marketplace. There's going to be people that have particular software and environments where they just want to keep x86, right?
Yep.
For example, if you've got servers that you're reconfiguring for different workloads, you probably need it to stay x86 just because there are going to be some of those workloads that are still very tied to the x86 architecture. There are going to be other places where ARM fits. I think in this AI area, it's a much more level playing field, and it's going to be down to the innovation across the marketplace as to how they pick and choose not just the CPU, like you were saying, but also that vector engine, the matrix math, whether they're going to use a GPU, whether they're not going to use a GPU, discrete NPU. I think we're in a period where we're going to see a massive uptake in innovation. And, quite often, we're seeing our technology sort of offloading AI acceleration capabilities from an x86 processor and an ARM processor. So again, back to my earlier point, I think people write a lot of column inches, but at the first place, it's about the system, stupid. And when you're pragmatic, you might see that actually it's a combination of technologies underneath to give you the right balance of scalar compute, NPU, and GPU if needed.
I think that's, again, capturing the real whereabouts for our customers, right? Going back to our collective experience at ARM, if you actually talk about, one, it's about the system, two, it's about the software stack, and three, it's about the efficiency with what you get done. Even ARM did not go full frontal into the server space on the compute side. It first went into the network appliance, then it went into the storage appliance, offloaded the true compute. The software ecosystem kind of caught up as it started becoming more and more a ready solution developing around it. But even those weren't just an x86 replacement as much as they were systems redesigned for the workloads that the data centers were trying to do. And
exactly.
And that kind of brings me to the related question, right? Which is, NVIDIA is clearly a visible investor in your latest raise. And NVIDIA has also showed how NVLink Fusion can be put across SiFive boards. Basically, the network and the communication aspect that actually extends this compute system around RISC-V. So this clearly should be a boost for the RISC-V based AI ecosystem, shouldn't it?
Yes. So, yeah, I mean, I think, NVIDIA's already getting their money's worth for this podcast, right? So, and especially as they spent no money on it, they're definitely getting their money. But in all seriousness, they've done an amazing job of pulling together a technology stack, right? And I think, that's hardware, software, defining interconnect with NVLink, and I think, my view of it is, I think NVIDIA is very pragmatic. They see that they're going to want to sell their GPUs, but they recognize that there's other use cases where actually customized platforms and enabling those customization things and getting to feed into the NVIDIA ecosystem is a better place for them to go for whatever, for their business reasons. So just to highlight what you said that's going on in the world of RISC-V. So NVIDIA, middle of 2025, announced that they were porting sort of the control elements of CUDA over to RISC-V that would allow a RISC-V host to sit in an NVIDIA-based platform. We announced in January 2026 that we would be planning to build some next-generation processors that would provide that connectivity from our CPU into the NVLink Fusion ecosystem. So I think it's really exciting. I think it comes back to my point I made a few minutes ago about empowering innovation. I think NVIDIA is saying, look, we've got our own technologies, Vera and Grace Hopper historically and Barrett Blackwell. We've got that. You're wanting to do something else for whatever reason. They've doing work. If you go to their website, they've enabled a few partners around this customized CPU capability alongside NVLink Fusion. That includes Intel. It includes us. It includes ARM. It also very recently includes Marvell. So I think at one level it's saying, look, the field is open. go knock yourself out with innovation. And we're not going to be telling you that you have to use x86. We're not going to be telling you have to use ARM. Feel empowered to use any of the architectures and then go innovate away. And we as NVIDIA are committed to enabling you to then get into that NVLink Fusion ecosystem and take the benefits of CUDA and all that sort of good stuff. And I think beyond that, anything else in terms of their investment in SiFive, I think it's too early to talk about, and there's other bits. But I think those are the big picture things of, I think just getting RISC-V ecosystem to a place where it's no longer a barrier for being able to participate in that ecosystem.
That makes sense. And for obviously that's music to Baya's ears, right? That what Jensen said at GTC versus also what he's doing, like both words and action are moving around the enablement of the ecosystem, but really
right.
the direction is that the next generation of compute is not just about compute widgets, but really tight coupling of that with efficient data movement across them, right? NVLink clearly showed how the scale up architectures would move, and that has driven a huge amount of kind of growth in the marketplace itself. You're seeing parallel standards like UA Link come on board, as you know, and eSun, and we're kind of in the center of that problem. How do we solve efficient data movement, right? And it is not just the traditional architectures that said, okay, this is the GPU, this is the network stack, and this is a scale out and this is scale up. But at the same time, you're beginning to see the transition to what are effectively optimized for purpose solutions, right? And so as we look at these purpose-built systems rather than one size fits all, I'm sure you're kind of at cheerleaders for that, right? So what does optimized for purpose mean in practice to you? And where do general purpose architectures, compute architectures break?
So I think there's so just to reflect on your comment, I think over the last year and a half of time, I've certainly been hearing, I'll go into a company and I'll talk about where we're going with our CPU cores, and I'll talk about spec int, and we can get into synthetic benchmarks a little bit later. But I think there's so much more concern about how I'm going to move data around, and matching bandwidths and architectures for CPUs, coherent interconnect, and memories for a particular workload. I saw, a few years ago, and I won't mention the name of the company, but people were putting down hundreds of cores previously, and they just weren't able to feed that beast, and you ended up with a whole load of dark silicon that wasn't able to be used just because you just couldn't feed those CPU cores. So I think we're seeing a lot more about people starting to think much more and challenge us on bandwidths inside the SoC, increasingly to look at chiplet architectures for some various reasons we can go into if you like, and then even starting to look at, you said in the previous podcast with Ty, looking at system to sit inside a rack and then between racks. So what do I see is breaking? I've seen people that firstly, the way processor architectures work, you have an instruction set, and all of these AI things are coming along with new models. People are looking at how you speed them up with maybe not having quite as much accuracy. So they're looking at different bit lengths. And so you saw all of this sort of work around int4 and int8, bflow 16. It's very hard for the general purpose processor architectures to keep up with that, right? And I think what's really important, and it was grilled into me in a previous company, is like you put something into the instruction set into a general purpose core, it's around forever. So you've got to be very careful about picking the right things into that CPU, because you're going to have to do ongoing support. And I think if you look at the world of AI, it's very hard right now. People were looking at optimizing for CNN models, and now it's transformer models, and people are looking at sparsity and these different bit lengths. People are already saying, well, some people are, it's the death of the this type of transformer, and we're going to move to something else. In that environment, unless you put a whole load of bloat into your main general purpose CPU core, it's a very challenging thing to go off and support. So what we see is people looking at just picking the things that they want for their workload, and again, because it's underneath an API, they can do some things and provide a sandbox way for their software to go and support that particular hardware, and that way they don't bloat their die size. And again, it's something that as things evolve, you can then say, well, do I throw it out? Do I keep it? But it's not. I think for a general purpose architecture, to try and keep track of all the things in AI, I think that's a big challenge. The second thing is people pick a CPU and they think that they're going to use a certain amount of memory with it. They think they're going to use a certain type of I/O configuration, and within 18 months, it's completely changed, right? You look at the people who originally built up CPUs thinking there was going to be a certain amount of memory, or GPUs thinking you could only attach a certain amount of memory. This whole memory wall problem. A lot of people are like, actually, I want to be able to add more memory. And you got people trying to sort of challenge that CPU to memory ratio that I think is a lot harder to do if you're going to a pre-packaged CPU or an SoC. So I think you see things like that CPU to memory ratio, the adoption of new AI algorithms. And again, you're not wanting to take everything on, so you can't bring a kitchen sink all the way through. You just look at HBM and DDR and how things have changed over the last few months in terms of pricing on memory and availability of memory. We talk a lot about data centers here, but if you think about the automotive space and you've got 5 years to design your next chip, and then you've got to deploy that for a following 10, how can you even predict this market at the moment in terms of what's going to be the right memory subsystem in 1 year, let alone 5? So I think those are the bits where, and one of the reasons why we start to see things like chiplets, where there's, back in the old days, because I am old, I used to call PCI Express get out of jail free card, right? And that was because around PCs, any new peripheral that would come out would first be targeting the PC space. And so people would, you wanted a USB controller or an Ethernet switch, it came out on PCI Express. And so if you designed a CPU, you'd have PCI Express, and something new came along, you had a really good chance that that design would be able to support it. And I think what's happening now is, now that the server space, and more specifically the data centers and hyperscalers, are driving this new innovation, I think what I'm seeing much more of is automotive companies, edge AI companies saying, I've got to sort of work out what my get out of jail free card is. I need to follow that sort of server ecosystem. And I think that's at least one of the reasons why we're seeing activity in chiplets, just to try and sort of mitigate the challenge of being wrong on these very long cycle projects, like building a car, building a satellite, building a robot.
It was quite comprehensive, and at the same time, if we're only scratching the surface in some of this, right? So one size doesn't fit all is clear. Systems are how you design it, and at the same time, it's not just SoC systems, it's really the entire system, because the supply of memory, what type of memory, what are the models that it's going to support, and timeline for all of that all comes in, right?
Yes.
I wanted to actually follow up with a different line of thinking, but since you've already opened up the discussion around chiplets, right? Clearly, modularity, scalability of fit for purpose components that you can actually build into larger systems in package is a goal around multi-die systems, right? Now, you could argue, does it actually simplify or just redistribute complexity? Right? And naturally, you're seeing that question. Obviously, for us, we've been looking at it from the developer's perspective or designer's perspective. How do you help them partition it into the right sets of chiplets? How do you attribute that complexity? Give us a little bit about what you're seeing in the industry for that, right? So what are the key challenges around chiplets? How do you see companies like Baya or the other EDA vendors trying to help it? And how does actual data movement, both on die across multi-die, factor into the next generation of system design?
Right. So, I think, especially with AI, I think there's a few things, right? So firstly, and you can pick whatever data analyst you like, but a 2 nanometer monolithic chip is really expensive, right? Whether it's $500 million, $300 million, it's a very expensive proposition. And if you are a hyperscaler, and again, maybe to go back to a mistake I made at ARM, we were originally thinking, why would people build a chip for a server? Because there aren't that many servers built. Back then there was maybe a TAM of 10 million chassis. What we missed was if that chip actually enables so many more sessions, each of which are being paid for by an end user on a per hour basis, the ROI isn't necessarily on the chip, it's what it enables at a system level. And so, clearly, if you're those sorts of people, you can justify that expense if it drives down, gives you competitive advantage on tokens per dollar and things like that. But if you're somebody else, how are you going to, one aspect of it is, how are you going to make a return on $300 million? That's just taping out the chip, let alone the ongoing manufacturing things, right? The second aspect is the cost of being wrong. Just because markets are moving, people that were designing for a particular DDR version a year ago are now starting to say, actually, I think I'm going to have to design for some HBM, because at least that's where there's going to be some products built, and maybe they're going to be expensive. So I put those in the cost of being wrong aspect. And so if I come to an automotive company, one use case is I'm going to build a base die that has the capabilities for the basic car. And I'm going to be able to use that same electronics and expand up CPU compute, expand up AI compute, maybe expand out some other functions too. Maybe I add more cameras, maybe add more sensors, whatever. But I have a base die that fits the needs of my base car, and then I can scale up the platform. So I see that in a number of applications where then, instead of having to do a chip and get an ROI just on one segment, you start to see it going across several. I see a similar thing in markets where everyone's very excited about robotics, but it's so new. I don't think anybody's worked out exactly what the right recipe is going to be for that perfect SoC. I think there's price being wrong, amortize the cost of one chip across multiple platforms, so that you have a little bit more of a chance to get your money back, get an ROI. And if you think about cars, think about being able to do certification for one of those platforms. You get into cars, and people will argue about a few cents difference on a chip or whatever. At the end of the day, it's the 3 years of certification and all of those costs and proving that it does what it says on the tin. That's where the real cost is. So what I see is some of the most pragmatic OEMs saying, you know what? This chiplet architecture costs me a bit more as a base thing, but I'm actually able to shave off multiple years potentially off my investment because I've got that base platform certified. And then when I have to certify the next thing, I say all of that other stuff is done. I just need to certify this expansion capability or this expansion capability. So that's a sort of some of the why for chiplets. I think on bandwidths and things like that, that's probably a question that you might be a little bit closer to than myself. I mean, you clearly lose something on latency as you go off chip or as you go across optical. Some amazing technology on optical as people look to connect GPUs together and share models and stuff. You're probably close. So I know there's degradation, but in terms of exactly where those trade-offs are, you're probably closer to that than me.
No, indeed. I think we do see this, we talk about communications at nanometer level, at millimeter level, at meter level, and kilometer level. Yeah. And in a lot of ways, you've already captured some of the key benefits of chiplets, right? So one is as reticle sizes don't scale and chips get to that level, cost increases for yield. Things like I/O, things like different types of SerDes don't need to be in the latest process technology if they can serve the purpose. You have other components that you can reuse. Plus, if you build it modularly, you can build out much larger systems rather than waiting for one giant SoC. But along with that...
sorry to interrupt. And if you're wrong, right? If a market moves... you don't have to redesign everything. It's okay. My memory subsystem has changed for whatever reason. I'll go fix that as opposed to fixing the whole thing.
Indeed, and alongside that, that's actually where I think we focus on the challenge of how do we help our designers partition it right. So if you're thinking about, you're familiar with the concepts of coherency and how it helps software, but it's also an expensive consideration when you build it, and especially if you split it across different chiplets or different chips, that adds a lot of additional cost if you have to carry a load of full coherency across. So how do you partition it? How do you level it? Becomes a very interesting consideration. How do you actually get localized movement on a single die versus things that go across dies are less latency sensitive? Those are all system design considerations, right?
Exactly.
And for us, I think what would be really interesting as we go through is talk about one of our common customers that is actually solving a number of these problems. They are in chiplets. They are actually solving bigger rethink system type of solutions. You want to delve into that a little bit?
So it's always good to sort of talk theoretically, right? But it's really great when you've got a customer rolling up their sleeves and doing real work with the combination of our technologies. So, limited exactly what I could say, but firstly, rather than it being an ARM versus RISC-V thing, it was much more of a ARM and RISC-V thing, right? Where they've picked the right thing for the right workhorse CPU for the right job. Secondly, if you look at that AI subsystem, it's a lot of cores, having to look at, system bandwidth. I mentioned earlier, rethinking that sort of CPU to memory rule, if you like, and really looking at how they put a lot of memory into a system. And I think the thing to talk about, one of the things I've liked about, I know this podcast where you're interviewing me, but one of the things I've liked about Baya is the is the modeling tools, right? Because I talked earlier about the cost of being wrong. And I'd love to get on my rant about TOPS in a few minutes on CPUs. But, it's absolutely pointless if your workload isn't going to be able to take full advantage of all this capability that you've got on the chip. And so this ability to profile flows of data, work out where they're going to be bottlenecks, look at trade-offs between different configurations and things. I think this is going to be an area in the overall area of EDA and with Baya where you're going to see AI help a lot, where people are going to be able to go through many more configurations of system modeling and saying, well, what about this structure? What about this? And come up with a much more quantifiable plan, as opposed to sort of like back a napkin and here's this amount of bandwidth and it's going to look like this. Actually really profile workloads far more accurately. I think it's going to be a great space for AI. I heard all sorts of interesting things going on at the leading EDA vendors there. But it really comes down to system level modeling. So I think those are the bits that I can talk about our mutual customer. I don't know what else you'd want to talk about. So.
No, I think this is great. I think it's actually a rubber meets the road kind of discussion, right? Which is clearly there was a multi-chiplet scenario. The modeling environments that Baya provides, the ability to actually do workload-driven, data-driven analysis, solves a lot of the headaches up front rather than later in the process, which is always the earlier you find issues, especially on system level understanding, the more cost effective it is, because as you go further into the process, it gets more and more expensive and potentially prohibitive. Right.
Yeah.
So,
and just picking up on it, the other thing I liked was, I mentioned earlier about TOPS. So, this theoretical sort of performance thing in the world of CPUs, as you know, people are actually still issuing RFPs in the automotive market for dry stone MIPS, and you're like, really? Come on. Something that just sits in primary cache. I mean, how does that give you a real feeling of how a system is going to behave? And clearly, where we have to move to is modeling of real workloads, right? And so I'm not saying TOPS is terrible, but it gives you a very rough guideline. But at least from what I've seen, that mutual customer, they had much more of a mindset of let's look at how my real workload works and profile that, as opposed to TOPS per dollar per square millimeter kind of metric. And I think for anybody that's thinking about AI, I think one of the big takeaways is having, and it's hard, but you just got to push your suppliers to get to that world of modeling real workloads. Otherwise, and you know this, Nandan, from some of the time you spent in the UK. In London, in the underground, they have these subway trains, right? And there's sometimes a distance between where the train stops at the platform and the platform itself, and there are all these signs saying "mind the gap." And my sort of analogy here is, TOPS versus real wide performance. There's a gap, right? And it becomes even more complicated when we're not just talking about the CPU, because we're having to think about the memory subsystem, the interconnects, and all of those pieces together. And that has a potential to make that quite a big gap, to the point where you maybe couldn't drive those trains in London anymore. You'd be sued. So, you got to really think about system level modeling, and you've got to do it on real workloads as opposed to synthetic stuff. That'd be my summary.
And in fact, I think your point being TOPS per watt doesn't necessarily translate to equivalent tokens per watt or tokens per dollar. Really, It is much more workload driven.
Yeah.
So I think this has been a pretty energizing discussion, right? And it's very clear that in the world of AI, it's been pushing us into the new era of computing. It's not just about fastest processors or even the architecture itself. It's really about finding the right fit on a system level view. And everything that has to come together, compute, memory, interconnect models, and system at scale rather than particularly the widget that you're talking about, right? And what stood out for me, which I think is the mantra you use, this is not really about a single architecture or a single approach. It is going to be defined by how we integrate, adapt, optimize for purpose, and really enable the innovation that drives that next level, right? And so ultimately the winners are not just ones that build great chips, but build complete solutions.
Yeah, and I think there's three things. I know those are great points. I think the first thing is you got to plan your get out of jail free card, right? Because in this AI world, something's going to change in the next 6 hours, let alone in the next 6 weeks. So, some of the best companies I've talked to go into scenarios of like, hey, if we bring out this product in 3 years' time and it's failed, why was it a problem? And then they try to build those scenarios for it. And that might be pick a chiplet architecture with expansion, with all of those. There are challenges, right? There's no such thing there as a free lunch. But planning for that expansion, even if it costs you more as the base platform, I think where we are in the world of AI, I think it's prudent. And I think the other one is around. It's about the business, stupid, right? So if we go back a few years, there was the world of IoT, and people were building connected systems because they could, right? Connected toilets that connected to Bluetooth. I mean, it didn't make any business sense, in my opinion. And I think, just because it's AI doesn't make it a good idea. And I think, there's a lot of companies at the moment that first thing with AI over the last few years is I've got to get something out because my CEO is telling me, my board is telling me I've got to get an AI platform out. So what's it going to do? I don't know. I got to get an AI system out. I think, we've got to challenge ourselves, not just the business folks, but in the engineering area. We've got to really understand whether we got a value proposition here from a business perspective. I saw it all with the IoT stuff, and that's now folded in, and now all you have is better systems, right? The ones that have lasted, they have connections and they deliver those values. And my view of AI, after all of this, I'm going to add AI to everything and I'm going to rename my business units with everything having AI in it. I think at some point we're going to get to a place where AI is an integrated thing and they're just better. And I think that comes with starting with a look from a business perspective first.
Cool. Any parting statements before you leave when we wrap up?
I think that was probably
good
reasonable.
Yes.
Just trying to think of anything else. I think that's it. I think I threw in a couple of controversial things. What question did you wish you asked me that we haven't done yet, Nandan?
No, I'll leave this one out. I think we can do that after we finish this call. So Ian, thanks for joining us and sharing your perspective. And of course, all the best to you and to SiFive as you forge your next path. I mean, certainly this seems like a shot in the arm, no pun intended, on where you're going next.
The hard work starts now. The hard work starts now, for sure. And thanks again for the opportunity, Nanda.
Thanks, Ian. And thanks for the listeners for tuning in to Tech Threads.
Thank you for listening to Tech Threads, Weaving the Intelligent Future podcast. Join us monthly for insights into the evolving tech landscape and the future of chiplet technology. If you enjoyed today's episode, don't forget to subscribe and share it with your network. And stay tuned for more expert discussions. Let's weave the intelligent future together.